Section 6.1 is called Approximating Integrals Numerically. This section in particular, I think your textbook has some nice explanations for some of the fine details of what's occurring when we're approximating integrals numerically. So I would encourage you to do the reading that I assigned this week. This is a really important tool to be able to use because most integrals, in fact, are very difficult to try and do by any sort of algebraic technique. We're now going to see this as a strictly numerical method. So in the last section, we created the rectangles, we looked at the graph, and then we generated the approximating sums. Well, there are patterns to all of these, and you don't actually need to have the graph. You can break the process down just in terms of numerical calculations, which is why this is called a numerical approach. At the beginning here, you have a summary of each of the approximating sums. So for instance, whenever you use a left approximating sum, because you're using the left endpoints of your subintervals, you're going to use the very first endpoint, which we're going to call x sub 0, and then we're going to leave off 1 at the end, which is why you're going to see x sub n minus 1. We're going to leave off the last function value. When we do a right approximation, things shift to the right. So we leave off this x to the 0 endpoint and instead begin with f of x sub 1. And we will go all the way to the very last endpoint. The trapezoidal sum, here's a formula for doing it, and then you've got one for the midpoint sum as well, but notice instead of using x, we switch to m sub 1, where m sub 1 is the midpoint of the first subinterval. So what I'm going to take you through now is how to do what we did in the last video with the graphs there, instead just doing it straight up as a calculation. I modified example 2 slightly. I wanted to do another one by hand. Again, practice is helpful. They did theirs using technology. We are going to practice the technology also. All right, so for part A, to calculate this integral, I can use fundamental theorem of calculus, which says the antiderivative is negative cosine of x evaluated from 0 to 1, which equals negative cosine of 1 minus negative cosine of 0. So you would want to have a calculator that's in radian mode. This is going to be a messy decimal. And then you're going to add to that or subtract a negative, same thing, cosine of 0. You will get approximately the decimal 0.4597. Now we're going to write out the approximating sums. So here's how you do that without any sort of graph. You're first going to do the width the same way that we have. This integral goes from 1 to 0, and we're told to use 4 subintervals, and I know that because that's the little subscript on each of these. So I'm going to do 4 subintervals, so the width of each rectangle is 1/4. All right, so now to write out the left approximating sum, each width is 1/4, so I start by putting that there. And I'm going to go back up to the formula for a moment. You can see here they have chosen to put their width at the end. I'm just more used to whenever we factor that factored thing goes in front. It doesn't actually matter. But now I'm supposed to use my first endpoint, my second endpoint, my third, so forth. Okay, so I find it's helpful to at least like draw a little number line out and think about it. I'm integrating from 0 to 1. The width of every rectangle is 1/4. So I've divided my segment into 4 pieces, and I can see that the values are 1/4, 1/2, and 3/4. So when you're doing a left approximation, you're using the left endpoints of each interval, which are these right here. So that means in terms of writing out my sum, I'm going to be calculating f of 0 plus f of 1/4 plus f of 1/2 plus f of 3/4. And notice how I'm leaving off the last endpoint. That's what this x sub n minus 1 means, is we're not going all the way to x sub n. We're leaving the last one off. So in terms of calculation then, I need to do 1/4 of my function. My f of x is right here. It's sine. So I'm going to do 1/4 of sine of 0 plus sine of a fourth plus sine of a half plus sine of 3/4. You really don't want to round anywhere before the end of the problem. So you're going to type all of this in and then either multiply it by 1/4 or just hit divide by 4. Those are the same thing. And you will get your left approximation should be to 4 decimal places 0.3521. Looks like an underestimate. The right sum, going back to my little number line, everything shifts to the right. So I'm now putting a box around the 4 values that I'll be using for the right approximating sum. So it would be 1/4 of, and I'm going to skip right to putting the signs in there. And again, going back up to the formula here, that's what this is saying, is I go all the way to the last endpoint, but I don't begin at the first one, x sub 0, I begin at x sub 1. I begin with one endpoint over. This is just calculator work. Type it in 4 decimal places, you should get 0.5625. And again, make sure your calculator's in radian mode. For the trapezoidal sum, you can go back up here, up top, and follow along here and use this version of the formula, or you can do it the way that we did it before, which is equivalent, which is to say that it's the sum of the left and the right divided by 2, which creates their average. I have the sum of the left and the right. I can factor out the fourth. And now I'm looking at these sums, and you can see sine of 0 appears once, only in the left sum. Then you can see that 1/4, 1/2, and 3/4 all appear twice. And I find it easier to do this than to memorize the weird looking formula. And then at the very end, sine of 1 only appears once in these two sums. So that sine of 1 whole thing gets divided by 2. All right, so again, calculator work. For my trapezoidal approximation, I get 0.4573, and that takes us to the midpoint sum. Again, you can go back to the formula here, which reminds you that you need the midpoints of all your subintervals. When I'm doing midpoint, I need the function value halfway between each of these intervals. So halfway between 0 and a fourth is an eighth. And then, like we saw before, the rest of these are now going to be the odd values. So 2/8, of course, would be 1/4. So this is 3/8. 1/2 is 4/8. So this is 5/8. And this is 7/8. So those are the values that we would be using for the midpoint sum. And the width of every bar is still going to be that 1/4. Every rectangle is still a fourth. And we're going to add together f of 1/8, 3/8, 5/8, and 7/8. Oops, forgot my f. That's the same as putting a sign where all those f's are. When you put that into the calculator, you should get this estimate to be 0.4609. Okay, so you can see without drawing the graph, we're able to numerically calculate our approximations. And in this particular case, part C wants us to compute the approximation errors. In other words, we want to judge how close did each of these come to accurately finding the value of the integral. And the way you calculate approximation errors is simply this. You take the actual integral value, which we do know in this case, You subtract the approximation, and we put that inside absolute value because we just want to make it positive. If they're overestimates, they would be negative. If they're underestimates, they'd be positive. We just want to switch them all to positive so we can compare them. I've just summarized our values from part B. So in part C, we're now going to perform this subtraction of actual integral value minus one of the approximations in the absolute value. So for instance, our exact value for our integral we took as 0.4597. I'm going to subtract the left approximation, 0.3521, and I'm going to keep it in absolute value. So this ends up giving us an error of 0.1076. I'm going to go ahead and set up and calculate the rest of the errors. So here are the calculations in the results. In this case, left was the furthest off. Right was a little bit closer to the actual value. And then notice the trapezoid is significantly better than that estimate, and significantly better than that estimate is the midpoint. You can see it's only off by 12 10,000ths, I guess. So pretty close, pretty accurate. Now, we're only able to judge that accuracy because we're able to calculate the integral in the first place. And if you can calculate the integral in the first place, you can do it exactly. So these approximations are not really necessary. One way of controlling the error and trying to minimize it when using the approximating sums is to trap your integral value between two of the sums. Here we've got an integral from 0 to 1 of sine of x squared dx. Now this is one that actually we don't have a method to directly integrate. So this would be a time where you'd be relying on approximating sums. In example 3 in the book, they go through calculating these. Again, we would use technology. You can use the Riemann sum calculator that you saw in the last video to generate these. And it says use these numbers to trap the integral. I've provided the graphs here again just to help clarify things. If you were going to calculate the integral from 0 to 1, so from this point to this point, by creating rectangles. Now I know this says this is an approximation with 100 rectangles, but just for purposes of discussion, I'm going to keep it to 4. If I were to draw the left Riemann sum, it would look like this, where the left endpoints are on the function. And you can see that that creates an underestimate because this curve is increasing. So this one is an underestimate, and the right approximation turns out to be an overestimate. And again, you could doodle on the graph and show that the rectangles are going to exceed the area under the curve. What this example is going to suggest to you is now let's trap the value of the integral between the underestimate and the overestimate. So I'm going to use the left value and know that my exact value of my integral will be between that and the right value. So you can see, I know my exact value for my integral is somewhere between these two numbers, which is a pretty tight trap, right? There's not a lot of difference between 0.3067 and 0.31448. Oh, I lost a 0 in there. Sorry, my bad. So that's a pretty good trap. When we actually use midpoint or trapezoid sums, remember with these, we'll look at midpoint, for example. Again, I'm not going to do 100 rectangles, but if you take the middle of the interval to create the height of the bar, both midpoint and trapezoid at times overestimate and at times underestimate. And it depends on the geometry of your function. You can tell from the values that the overestimate in this case is the trapezoidal sum because it's larger than the midpoint sum. So this one's going to be an overestimate. And the midpoint sum is going to be an underestimate. These two work as a pair as the left and right do. So again, the thought here is I can trap the value of the integral. I know it's going to be between the midpoint approximation and the trapezoidal, which means it's going to fall between 0.31026, 0.31028. And this trap is even tighter than the last one in the sense of the midpoint and the trapezoidal are so close together that the actual integral has very little difference in terms of the values that it can take on. So that's the idea of trapping the value, is getting a sense of what the value must be by trapping it between two approximations. That brings us to Theorem 1 and Theorem 2. Theorem 1 says, suppose that your function is monotone. Now, this theorem only applies for functions that are monotone. Monotone means it's always increasing or always decreasing, but not both. In other words, on the interval you're integrating, you're not going to see it like waver like that. We're talking about functions that just are increasing all the way or decreasing all the way without switching. So in that instance, for any positive integers n and m, your number of subdivisions, okay, notice your subdivisions don't have to be equal for left and right approximations for this to work, although very often we do keep them equal, but it's not necessary for the theorem to be true. We know that we can trap between the left and the right. And what you are going to want to add in here is that the left is always going to be an underestimate for increasing functions, like you saw up here. So this is for increasing functions. They just reverse places when your function is decreasing. In that instance, the left approximation would be an overestimate. The midpoint and the trapezoid sum have to do with the concavity of the curve. If your function is concave up, then your trapezoid will always be an overestimate, and your midpoint will be an underestimate. And again, that's what we saw with this example. Hopefully you remember concave up are things shaped like this, where the cup is opening up. It says here your trapezoid is going to be the overestimate. So that's this first trap. Anytime you're concave up, trapezoid is over. And then anytime the concavity switches to concave down, the trapezoidal becomes the underestimate. So we've got this idea that we can trap an integral. To find an even better approximation, Theorem 1 tells us that for any monotone function, the exact value of an integral is between the left and right approximations. The trapezoid sum does find an average of those two. So it's kind of finding a middle of those two values. So we take the average of those two to get a good estimate. Now, Theorem 2 tells us that the exact value of certain integrals, where you're either concave up or concave down, will be between the trapezoidal and the midpoint. Now, generally speaking, the trapezoid gives about twice as much error as the midpoint on the whole. So therefore, rather than just take the average of these two to get a better estimate, we're going to do what's called a weighted average, in which we count the midpoint more because it produces less error, and we weigh the trapezoid sum less because it commits more error. So to get an estimate based on these two sums, we're going to do an average as a weighted average. And you can see here that the approximation that we get, which we're now using S because this is called Simpson's rule, for 2n subintervals, we'll come back to that in a second, we're going to give a 2/3 weighting to the midpoint sum and a 1/3 weighting to the trapezoid sum. The reason your subintervals all of a sudden doubles is because the trapezoid sum, remember, is using the endpoints of the intervals, while the midpoint uses the point in between those. So you're creating twice as many subintervals when you take an average of those two. So let's look back to example 2. We're going to use Simpson's rule to approximate the value of our integral. So going back to example 2. From 0 to 1, let's think about what the graph of sine looks like. Okay, that's what your sine wave does. Now, pi over 2 is the same as like 1.5 radians. It's 3.14 divided by 2. So we know that this integral that we're trying to approximate is increasing and it's concave down. So let's use the fact that we can trap it and do a weighted average to find out an even better approximation than any of these. So again, this is Simpson's rule, which doubles the subintervals. You give a 2/3 weighting to the more accurate sum and a 1/3 weighting to the less accurate sum. Okay, now in our problem n was 4, so that means I'm actually calculating Simpson's rule with 8 subintervals. I'm going to take 2/3 of the midpoint approximation with 4 subintervals and 1/3 the trapezoidal with 4 subintervals. So if you take 2/3 of 0.4609 and add 1/3 of 0.4573, it turns out you get 0.4597. And notice that's the exact value of the integral. So Simpson's rule gives us a highly accurate way to use a weighted average of midpoint and trapezoidal sum to come up with the best approximation. So just a friendly reminder, again, I think it's really helpful to go and read some of the explanations that the textbook has. It'll give you a really good understanding and some more explanation for why these things work.